Ben just put it on my desk. Knowing Ben was on his.
Okay,
Wait.
our last topic of calculus. I don't know why that came up.
Is how to turn off the clock.
Genius!
Do we happen to need a calculator outline?
No.
No.
No, we don't.
Just wondering.
Looks like it's worth
So, we are going to
Sorry.
do the calculus of our parametric curves. We're going to learn how to define a polar curve parametrically, find the derivative of a polar curve, and find the area between two polar curves.
I don't know, he's so good at calculus. He just draws calculators.
I was drawing my brain.
So when we have a parametric equation, a parametric equation is defined as x of t, comma, y of t. Well, if we're working with polar coordinates, we already know something for x and something for y. We have some formulas for them already. What do we know about x and y in polar coordinates? Okay, random thought. Evelyn was saying, not Evelyn, Eliana was saying how she didn't like how x was cosine and r was sine. There actually is reasoning behind it. Like when you draw the unit circle and you draw the cosine, it forms like a bow shape, and the bow shape was called cosine in like ancient Greek. And when you draw sine, it forms a different shape, and it was, so there was reasoning behind it. Just so you know.
So it wasn't something the physicists just made up.
But
No.
how did they relate that shape to x? And the other shape to y?
In ancient Greek, their x's looked like
Because they had
that.
decided that direction was x and that direction was y.
Yeah, Hercules declared it or something.
So Descartes
Hercules.
decided.
It has to be Hercules.
This way is why.
He was like the only man that could be like super strong and intelligent.
Yeah,
Okay.
so for you, like,
Have you ever watched
women-
Hercules? It's kind of dumb, actually.
You realize the Disney one's like,
Well, you know what?
Amazing
Nobody
clothes.
actually watches anything else.
the only good thing about the Disney one is
They're
that he
super
owns up
hyper,
Scar.
even though it's 2 days away.
2 days away?
The
That's
only
2
good
days
part about
away.
Hercules is they have
so
sauce.
I'm getting excused Friday.
Okay,
I wish I could too.
can't believe I have to say this to my calculus class. Let's refocus. Pay attention up front.
Sorry, we're talking about thought.
No, they're
Like
saying
everyone to
it's
realize
not
that
right.
the first time she said
saying,
this,
are you
kidding me? I've snapped 2 million
You should be
times.
impressed.
Well, then no, my
Yeah,
hand
usually it's not a huge deal when there's
I
only
don't
6
even
of us,
break
but
my
when
hands.
all
I
6
just
of
hold
us
my
are
back
distracted
and
at
my
once,
side. It's like Sunday.
then that's
There's
a
only
problem.
5 of us,
So
because I'm
Josh.
focusing.
Me
Eliana,
too. I'm focused.
It's refocus. Okay, we can use these to define a polar curve parametrically. Our polar curve would be x of theta
That's awesome.
and y of theta, because r itself is already a function of theta. We're going to end up replacing r so that all we have is thetas. So x of theta would be the r cosine theta. This would define our curve parametrically. And parametrically, what do we know about the derivative of a parametric curve? We have a formula to find the derivative of a parametric curve. What would dy dx be? dy dt over dx dt, except now we're in thetas, so dy d theta over dx d theta. But when we're doing stuff parametrically, I can talk about a lot of things. I could talk individually about dy d theta. I could talk individually about dx d theta. And I could talk originally about r. I could find dr d theta using our original r function. So with parametric, or at least polar parametrics, I can find 4 different derivatives to talk about. And they could ask you about any of the 4.
So the dy dx, dy d theta, dr d theta, dx d
The fourth one is hidden.
Oh, okay.
So suppose we have a polar curve r equals 2 sine of 3 theta. Let's say, first of all, I just want to find dr d theta. That one's the easiest because I already have r's and I already have thetas. I don't have to do any of the parametric defining. I just can take my equation as it is and find the derivative. So what would dr d theta equal? Derivative of 2 sine 3 theta.
Ours just is.
Is that a calculus?
Calculus, yes.
6 cosine.
Okay, 6 cosine 3 theta. Why did Emma say 6?
Because the 3 you have to times to the 2.
Chain rule. Why don't I need, like we were doing implicitly?
You got circle.
It is the Greek letter theta, commonly used to represent angles, or Greek fraternity houses.
No.
Okay?
No.
So, when we were doing implicit differentiation in our warm-up, we would multiply by the derivative of the inside, and that would be d theta, which would cancel out. So we don't really have to worry about the implicit part here. Now this can tell me, dr d theta would tell me how fast is the radius changing compared to the angle changing. That's why we have it labeled this way. So if dr d theta was negative, what would we know about the radius? Thinking about graphing on our polar curve, our radius is from the center to whatever point at whatever angle we're looking at. So what would happen if r is negative? We're changing the radius negatively.
Would it?
The flipping part would be if r itself was negative, but since we're talking about dr d theta being negative, we're deciding how does that change my radius? My radius can either move and get bigger, or my radius can move and get smaller. So my radius would be getting closer to the origin. When the derivative was negative for a regular function, what did that mean about if dy dx was negative? What did it mean about y? This was from like the beginning of the year. We had to use it on our line test. If I did this on my line test, what do we know about the point here? It's a minimum because we went from decreasing to increasing. So when dy dx is negative, our function gets smaller. When dr d theta is negative, our radius goes closer to the center, goes towards the origin. So if dr d theta was positive, what's going to happen?
Further away.
It's going to get further away from the origin. So on polar coordinates, we're trying to compare to the origin what's going on with our radius, not compare what's going on with our function overall. Okay, what about dy d theta?
And would the line, the angle wouldn't change, it would be in the same spot, it would just go.
Well, it's talking about as your angle is changing,
Oh.
what's going on with the radius.
Oh, okay. So as the angle changes, then it would go.
Yep. So we could find, if we found an interval where it was negative from like pi to pi, well, I can't go pi to pi halves, pi to 3 pi halves. If I said the derivative here, dr d theta, is negative from pi to 3 pi halves, we'd start further out, and then our function would be getting closer to the origin as we go. So B, find dy d theta. First I need y. I don't have y right now, but what do we know y equals?
R sine theta.
R sine theta. I think I should have maybe given myself more room. Well, I can't differentiate right now because I only want y's and thetas. But what do I know about r?
Equals 2 sine 3 theta.
It equals 2 sine 3 theta. Now I can differentiate this. What rule do I have to use though, or rules on this one?
Chain and
Pro-chain, product and chain.
how do you product first and then chain, or do you chain and then product?
Product first, then chain, because product is affecting more things than chain.
And then it's you product that you end up with.
Yep. So take the derivative of that for practice.
I figured it was.
So which one of you wants
Okay.
to get it for me?
So what's the derivative? What is dy d theta?
Sine theta, 6 cosine 3 theta, plus 2 sine 3 theta times cosine.
Good. That's what it is.
That's still your speed? That's still your speed?
Okay, now we need to do the same thing to find dx d theta. What do we know about x?
Cosine theta.
It equals our cosine theta. And what do we know about r?
2 sine
2 sine 3 theta. So again, we do product rule. It's going to look very similar to what we had there.
Product rules are
Just
fun.
did this.
Well, pro-chain, I guess. Dx d theta. So low d high, cosine is low. D high, we've taken the derivative a couple of times now, so we don't need to do it again. We know it's 6. Why did I put equals times? 6 sine 3 theta. Plus high d low.
Wouldn't it be 6 cosine 3 theta?
Yeah, wouldn't it be 6 cosine 3 theta?
Yes,
Good catch.
Yeah.
thank you. Plus high d low, this would be negative sine theta. So now we know dy d theta, we know dx d theta. I could put this in parametric form. I could put these as, it looks like a coordinate, but it's really a parametric form of, we could find the position vector and the velocity vector. We would just write it in coordinate form. Yeah. Yes.
So you did say that the parametric equation is x of t and y of t. X of t comma y of t.
Yes. Or x of theta comma y of theta, since we're working with thetas on this one.
So it's the same thing.
In this
Just
case.
thetas. Yep.
Oh.
I could also talk about the derivative again. What if this derivative was negative? What is x talking about parametrically? Horizontal movements. So I could say, as my angle is changing, if this derivative was negative, x is going to the left. If it was positive, we'd be going to the right. What if I looked at dy d theta and said dy d theta is negative?
Up or down?
Up or down? Negative, our function would be moving down as our angle changed, if our derivative was negative. If it was positive, our function would be moving up as our angle changed. So notice on the last one, I didn't actually mention dy dx. Even though you guys know, because we talked about how there's 4 derivatives I could talk to you about, that we need to get dy dx involved. When it asks us to find the equation of the tangent line, just like parametrically, the tangent line is always based off of dy dx. Since we're still in the xy plane, to find a tangent line, I need an x value, a y value, and I need the slope using that x and y value. So even though it doesn't state dy dx, we should know, hey, this is dy dx, because it asked us to find the tangent line. And specifically, where do we want to find the slope at? Pi 6. And if we're finding a tangent line, what else do we need besides the slope?
X and Y.
X and y. How am I going to find x and y?
Found in the last one.
Plug in pi 6 into the original. So I can find x of pi 6, which was, let's see, x is 2 sine
3 theta cosine theta.
3 times pi 6 cosine of pi 6. I can find y of pi 6, which would be 2 sine 3 times pi over 6 times sine of pi over 6. And I could find dy dx. How do we find dy dx from information we've already found up above?
You divide dy d theta by dx d theta.
Dy d theta divided by dx d theta. Now, just so we don't have to write it out a second time, because those were very long derivatives, I'm going to say, well, we know we're going to do dy d theta divided by dx d theta, and we're going to evaluate it at pi over 6. We use the evaluate sign more often in integration. It really just means plug it in. But we can use the evaluate sign in differentiation to be lazy. That's all it is. Laziness.
They counted on the AP test.
Yep, they would count that notation on the AP test. If you wrote this on the AP test and then said this equals 5.7 or whatever it happens to be, I know it's not 5.7, but just, they would accept that as correct notation. So, we need to plug everything in. Evelyn and Emma find x. Eliana and Melinda find y. And Josh and Ben find dy dx at pi over 6. Okay, x value. Square root 3. Y value. Derivative.
Please hold. Do you want a decimal?
Do you remember that one time we
Do you want
Either
a
way.
decimal?
This one, doesn't it come out like square root 3 minus something or something?
Negative
so.
square root 3 plus 1.
So,
Oh, negative and then everything's in parentheses, so I guess negative square root 3 minus 1 if you
or,
want. Negative 2.732.
5 decimal please.
Oh, 5.
Since we have to plug it back into something. So now we have an x, we have a y, we have a
Show me
slope.
what the x is again, and the y.
X was square root 3, y was 1. We write the equation of our tangent line. Y minus 1 equals our slope. You can write it either way as the decimal or the exact, times x minus square root 3. And just for fun, let's actually graph this so that you can see that it really is the tangent line at pi over 6.
I think Josh is going to be a calculus teacher someday.
So
He does stuff like this for fun. So he's going to be one of those teachers.
I'm going to move the 1 over.
Yeah, let me tell you.
Oh, you know, I wonder if we can graph both on the same. I've never tried this. So, because one is parametric, or one is polar.
Ben, I got your calculator.
I'm too short for this smartboard.
Oh, you have a calculator from last time.
So first we want to graph polar. It was 2 sine 3 theta?
Yep.
Wait, what numbers? 3 and 4. Oh, okay.
graphing the polar function.
Oh.
So what we found should be a tangent line at pi over 6, right? That's what we were plugging in. So pi over 6 here-ish, 30 degrees-ish. So we should get a tangent line about there. So now we want to graph just a regular function. Oh, hooray, we can do it. It was negative 2.70,
Oh, negative
73205.
73205, parenthesis, x minus square root 3.
Would you have to add the one?
Yes, you would have to add the 1 to plug it in here.
Hey, look at that. Yeah.
It's a necklace.
I know.
Kind of does look like one. Okay, so our tangent line is at pi over 6.
Sweet.
So does everyone have this before I move to the next page? Okay, so I'm going to have you guys try one. So this is taken from an actual AP free response question. Because the book doesn't have great questions for polar coordinates. It's just
No homework.
your homework is a worksheet.
Oh,
Good try.
it's good thinking.
So I didn't ask you about all 4 things. I just asked you one specific. So you're not going to be finding all 4 derivatives necessarily. Although if I do ask you to find dy dx, you kind of have to find dy d theta and dx d theta. But I want you guys to try this one on your own first. Yeah. Notice they did define dr dt equal to dr d theta. Those are equal to each other.
To us then. We actually have a pre-tour concert tomorrow.
Ah.
Well, listen to us.
I'm going to see Shrek at the junior high tomorrow.
What
It's
time?
at Evergreen Junior High.
What time?
I think 7.
Melanie,
Okay.
what time's the concert?
6:30.
Tomorrow, 6:30.
6:30.
Oh, man.
That's when all the
Sorry.
choirs start.
Last thing about polar curves is area. So area of a polar curve, I just have to say I don't really like it.
Oh, no.
I mean, the formula itself is not hard. The formula itself isn't hard. It's figuring out the stinking bounds that's hard. Like, the formula itself isn't hard at all. The area of a polar curve is the integral from alpha to beta of 1/2 r squared d theta. That is beta.
Oh.
So it's a Greek b,
That's how I'm gonna write my name from now on.
beta. Okay.
Why
So,
don't they just go A to B? Why do they have to say alpha to beta?
because we are discussing angles, almost all, like exclusively when you're talking about angles, you use Greek letters. Or, if I have 2 polar curves and I want the area in between the 2 polar curves,
I'm sorry. Okay. I can do that. Sure.
you'd have 1/2 the big outside curve squared minus the inside. So if we have 2 polar curves, the larger radius squared minus the smaller radius squared.
Right.
So again, the formula itself, super easy. Plug in r. They're going to tell you r equals blah. You're going to plug that into that.
It's just finding the balance.
Finding the bounds, not as easy. Finding the bounds. It's a pain in the butt. So let's say we want the area enclosed by r equals 2, 1 plus cosine theta. Now, if you're lucky, they'll tell you the bounds. There are problems where they say, find the area in the third quadrant. What would my bounds be if I was in the third quadrant?
It would be from this one
Pi
to this
to
one.
3 pi halves.
Pi to 3 pi halves.
Oh,
Okay.
good.
Yep, third quadrant. We showed the general idea. The general idea. Okay. This one, we need our picture first. They usually do provide the picture when it's asking an area question. Not always, but for the most part. This one, we're going to use our calculator to get the picture because I didn't write it down beforehand. 2 times 1 plus cos theta. Let's see. Doc B. Come on. Or not. Fine. No, not parametric. Last thing. 3. 4. 2.
Of what? Wait, what?
You missed the end of the lesson. Please subtract me. And I'm supposed to leave in 1 minute.
Oh, you have a track
Oh.
meet today? Good luck.
You know, I don't know if I'll end up being able to run
Oh.
Why not?
because I didn't turn my paper.
Ben, is there a guy named Chase on the team?
Chase, you.
He's really tall, kind of grungy looking.
Does he play an instrument?
Yeah.
Like really tall white guy. And he has like lighter hair. I don't think so.
I don't
What?
No, he has like dark hair.
Okay, there's the picture of our...
That makes sense. He's like, so describing. No.
You don't start describing them as they are on the team.
No, because I know a Chase. I just don't know if that's.
Now, circle-wise, we always start at 0 for our angle and go to 2 pi. This doesn't necessarily follow that pattern. Just because normally at 0 we're out here, doesn't mean that's where our graph actually started. So we cannot find our bounds. Like I said, the integral part's easy. And on the AP test, honestly, you get one of the 2 points just by having the integrand correct, by having 1/2 times 2, 1 plus cosine theta
When you said points, I thought you meant
squared.
Yeah.
like the one of the points.
Oh, sorry,
So I
no.
was like, what?
One of the points that,
Gotcha.
yeah.
That's called an
Okay.
integrand?
The inside, this is the integrand.
Oh, I thought you said integram. Integram.
So you get one of the 2 values just by having that. But we still have to figure out where to start, where to finish. And again, we can't figure out our angles just by saying, oh, this went in a full circle, kind of. So we must go from 0 to 2 pi.
Oh, you must.
That's not how it works. So on this one, it's easy to find a key point by thinking about the radius. There is one key point on this where the radius is special. Where would the radius be?
Probably where it like has a little peach. Yes.
Right here. What would the radius be at this point?
0.
0. Okay. Our radius here is 0. Well, I have a function. If I say, hey, I know my radius is 0, can I solve that?
Yes, you can.
Yes, we
I
can.
just was thinking of like Bob the Builder when he's like, oh.
So, we could divide by 2. We could minus 1.
I know, that's what I think every time I go on track practice.
It's funny, it's sorry, I had to say it.
And that could give us some values. It could actually give us multiple values. If we do inverse cosine of -1, what's the first value we think of?
What now?
That would be inverse sine.
She thought it.
Okay. It is. But then it threw my brain through a loop. So I'm like, wait, is it 3 pi halves? No. Inverse cosine of negative 1.
Here, I could do this.
Good luck, Ben.
Oh, that is a comment there.
Inverse cosine of negative 1.
Hi.
Pi. Okay? But I can find another value of that. Where else would inverse cosine? Not 2 pi. 3 pi. If we did another complete circle. 5 pi.
7 pi.
7 pi. Or negative pi. 9 pi. Over. Okay. So, I could say, well, negative pi also works, or 2 pi, so on and so forth. So we would do one complete revolution if we started at one of these values.
Wasn't it 3 pi, not 2 pi?
Yeah, it was 2 pi.
I was like, wait.
Sorry. Breakers. It's hard to talk and write at the same time, okay? Okay, so we could use these bounds, negative pi to pi, because that would give us one full revolution. Going to, starting at negative pi and going to pi would give us the entire shape because our point hits it twice. This will only work if we have that point where it kind of is the start and the end of your shape. So if we integrate this from negative pi to pi, then that gives us, where's my, sorry, I wrote this on so many different pieces of paper while I was preparing that I'm not sure which one has my answer now. $18.849. So we need one more example. We're on example 3, right? 2.
Well, technically,
Oh, because we did it twice.
No, we just did example
we did 2 examples.
Yeah.
one. Example one.
Yeah. That's fine. Let's say we have the polar curves r equals 2 and r equals 3 plus 2 cosine theta. So r equals 2 would just be a plain old circle, radius 2. R equals 3 plus 2 cosine theta. Will look like that-ish. Obviously a little more circular than I have. And I want to find this area where they overlap. And on this particular question, they also gave me that we intersect at 2 pi over 3 and 4 pi over 3. That was given. Now, circle-wise, we do know where a circle starts and ends. What are our bounds for a circle angle-wise? Where do we usually start our circle at? 0. And where does our circle end at? 2 pi. So we know this is the start of our circle, the starting radius. And this one, we're actually not even going to do the subtraction feature that we had. The subtraction is actually less useful than thinking about this logically. So I could keep traveling on my circle until I hit this point, because what changes at that point? Okay. Then the area of this shape is no longer given by the circle. This piece would be given by, I think this is a limacon. And same thing, until we hit here, all of this area is given by this formula. Does that make sense? So then the rest of my area would be from 4 pi over 3 until I hit my circle, or the end of my circle. So we're actually going to have to split this into 3 different integrals. We're going to have to have our integral that we started with. We started at 0. Where did we have to end our first integral?
2 pi thirds.
2 pi thirds. And what's our function we're using on that? R equals 2. So we have 1/2 times our function squared, so 2 squared d theta. Plus, now we need that middle piece. And this is, so we're so used to thinking left to right. This is why polar curves at least throw me off, because we're not thinking left to right at all. We're thinking in terms of my angle traveling on the circle, which for me really just my brain is like, no, that's not how it's supposed to work. So what would our next bounds be?
2 pi thirds to 4.
Is the plus plusing this next to?
Yeah, I just don't have enough room. Really, it should all be on one line. But
So you get
so 2 pi thirds to 4 pi thirds. But what function are we using to get that next piece?
3 plus 2 cosine theta.
So 1/2 times 3 plus 2 cosine theta squared plus, what should our last piece be?
To 0. Well,
To 2 pi, since we're starting at 4 pi thirds, since we're moving up. Even though technically it is 0 still. 1/2 times. And again, we're back to using our circle. If we again plug all of that into a calculator, which you know how to do, it would just take some time, but since we're running low on time, this would all equal 10.370. So tomorrow we are going to start reviewing for the test, but we're going to have to take the test when people get back from tour. So we'll have a review day when people get back from tour as well, and then the test.
so you're gonna have like 3 days of review.
I think we'll still just do 2 since it was a shorter. One before you leave, one after you leave, so the review is going to be split
What
over.
about those other 2
Oh, also, test corrections for the last test.
Oh.
Really, I should have made them do tomorrow, except I never announced that. So, the problem is that test did go on this term, but you guys are going to be going on tour, so I'll make them do next Thursday.
Yes. Thank you. Thank
But-
you so much. Best day ever.
I'd almost rather get them done before tour, so I didn't have to worry about it on tour. That's just my
Right.
opinion.
No, I know. I just.
But since that would have to be done tonight and due tomorrow,